Okay, so let's get started. Hello everyone. Welcome to the week 11th TS session for the TS session for the course Optical Spectroscopy and Microscopy, Fundamentals of Optical Measurements and Instrumentation. Um, and As you all know, I am Arjun and I am the TA for this course. So we are here for the second last week of this TA session. As usual, what the routine will be the same, where we'll be going over a brief recap of what happened in the previous week, followed by which we'll be going over some sample problems and we'll also be going over the previous week's assignment questions, which will be eventually week 10's assignment questions. So, Without further ado, let's get started. I'll just yeah. So we all know that over the course of this 10 weeks, what we have been learning is we have been learning more about light, more about optical phenomena, and by with respect to optical phenomena, we are learning more about the process of absorbance, fluorescence, as well as phosphorescence, and we are eventually what we started as studying optical phenomena through quantum mechanical processes, we slowly came into the application parts of it. How can we use light to develop optical instrumentation processes, and how can we use to construct uh, instruments which can use light in a way to image your specimens of your interest. So with that, we also came to uh, see about a lot of um, continuous lasers as well as pulse lasers, and slowly we came into discussing uh, beam optics as well as what goes into a confocal microscope. And slowly, with respect to that, in week 11, what we have been learning is we have been learning at what are all the instrumentation parameters that we need to check in a specific microscope. So what and all, and specifically what we are looking at is what are all the aberrations, what are all the irregularities that could be happening with respect to optical phenomena in a microscope. So those that was the main focus of this week's lectures. So we started by discussing something called as axial as well as lateral chromatic aberrations. So axial and lateral chromatic aberrations fall under the broad category of polychromatic aberrations. So these just mean that um, when we have light, which can be split into multiple light of multiple wavelengths from ranging, let's just say for example, ranging in the visible region. So what and all aberrations or irregularities can be formed due to the splitting of this light when the white light falls into the lens. So this is what is called as axial and lateral chromatic aberration. Mainly, if you can see different, if you split light into its respective components, each component of the light has a different unique wavelength. So, and we also saw that um, each wavelength of we also saw in last week's lectures that each wavelength has its own wavelength dependent there's a wavelength dependent refractive index with respect to each wavelength when we pass light through biconcave or a biconvex lens. So as a result, what happens is that um, the wavelength, like different wavelengths of light, split in different ways, and this splitting causes different kinds of aberrations. So when you look at axial chromatic aberrations, we look upon the optical axis, and therefore aberrations which act upon the optical axis are known as axial aberrations. So, for example, different wavelengths of light. So, longer wavelengths might converge at later points after striking a lens, and shorter wavelengths, is, for example, shown here, strike at strike much converge much closer to the lens compared to the longer wavelengths. So, these are called as your axial aberrations. So, um, these might cause different wavelengths of your light to be out of focus, while some wavelengths of the light to be in focus. On the other hand, lateral chromatic aberrations are aberrations which happen in the same focal plane. So if you consider the same focal plane here, aberrations which happen in the same focal plane are known as lateral chromatic aberrations. The implications of that is that you can visibly see that um, a specimen is expressing different components of the light side by side. So you'll be seeing leaking or fringing of light across a certain optical axis. So we looked upon certain polychromatic aberrations, and we also saw what do we need to build, what are all the necessary parameters that we need to build in order to improve the resolution of a microscope. And one such parameter that we came across was numerical aperture. Uh, how come uh, how come we increasing in numerical aperture helps in increasing the resolution of the microscope, thereby also increasing the imaging depth. So, following that, we also saw more about the lens maker's formula, where we saw in details about the wavelength dependent refractive index, um, and we further developed into. So, what we see here is a basic representation of the lens maker's formula. We further developed it into advanced terms using all the terminologies that we know. And following that, we came into something called as monochromatic aberrations. So monochromatic aberrations are the kind of irregularities or aberrations um, which are not dependent on the wavelength of the light. So these aberrations happen irrespective of the wavelength of the light. So we saw mm, more about the different types of uh, monochromatic aberrations, particularly your spherical aberration, your astigmatism, as well as your coma. And we also saw how to kind of negate, how to kind of neutralize this kind of monochromatic aberrations. For example, spherical aberrations can be um, negated by using planar convex lens, by or it can be switched by a biconcave or biconvex lens to a planar concave or planar convex lens to negate it. Similarly, your astigmatism is mainly caused due to irregularities in your lens surface. So astigmatism can be negated by um, polishing your lens. And apart from these monochromatic aberrations, we also saw something called as curvature-based aberrations, and we also saw about your pincushion or your barrel-based aberrations. And following that, we also saw more about your additional components which needs to be checked before running a microscope. Mainly, you need to check your PMT, which is your photomultiplier tube. You have to check for your detector gain, and we also have to check about your incident light, if it is giving low intensity or not. And we also have to check the histogram of pixel intensity, which gives us key information about how a microscope operates. And we also need to check about your external amplifier gain, which will determine your output of the sample. And apart from that, we discussed small topics such as your galvanometric speed, which is required to give your appropriate signal. And we also saw how scan area, uh, how how the increase in scan area is implication of your increase in the galvanometric pulse. And after seeing all of this, we got in the last lecture of the video, we also got a small demo on how a microscope works. Basically, we saw the different components of a laser system, and what and all safety procedures we need to follow while before implementing or before starting to work with this kind of systems. So that's all the short recap that happened for week 11. So we can have a short doubt session if you people have any doubts. Else we will proceed to discuss the sample problems. Okay, if there are no doubts, we'll go ahead with discussing some of the sample problems. So first question is, in the laboratory setup, what is the standard voltage range for a TTL pulse used to switch a laser diode on and off? So we saw that for different kinds of TTL pulse, we used to use different kinds of um, voltage ranges. It's ranging from 0.1 to 1, 1 to 10, and 10 to 100 kind of voltage ranges. So if you see any kind of range that falls into it, it's kind of 0 to 5. So the correct answer will be 0, 0 to 5 volt. Yeah. So it's kind of a straightforward question. Which optical element is specifically used to combine three different laser wavelengths into a single path? So there is this optical element. It is used to combine three different wavelengths RGB into a single path. Which one is it? So a beam splitter can't converge into a single path. Same goes for a concave mirror. Concave mirror is more used to diverge here. So the answer is dichroic mirror. So third question, according to the laboratory safety demonstrations, what is the best practice to avoid eye damage from lasers? And we saw from the last lecture, there is the introduction to a laboratory setup that in order to avoid eye damage, you should always do the alignment with keeping the laser beam out of the eye range. So the correct answer here is option D, adopting alignment habits that keep the eyes out of the beam plane. Question number 4. When aligning a beam to a lens system, mirror 1 is primarily used to control what? And this is also a pretty straightforward question, is the intercept or precision. Yeah. So for a telescope system to produce a collimated output from a collimated input, the distance between the two lenses must be what? So I think it will be better, best if it is annotated properly. Yeah. So let's just have two lenses, and the input of this lens is collimated, and the output of this lens is collimated. So in order to do that, what should be the distance between the two lenses? So for example, we know that if input is collimated in the first lens, so it would diverge, it will converge and meet in the focal length of the first lens. And after converging in the focal length of first lens, they will start to diverge. And after diverging, if they hit the second lens, they will once again be collimated in range. So if you want to get a collimated input as well as output, so the distance between these two lenses should be the sum of their focal lengths. So the answer will be f1 plus f2. So this is basically the sum of the focal length of the two lenses. Yeah, so I'll go on to the next question if no one has any doubts. What is the primary mechanical advantage of using a cage system over individual post holders um, in an optical setup? And it's also a straightforward question. The answer is option C, which maintains the cage system actually maintains the centering of relative centering of optical elements during focal adjustments. Seventh question. In the context of fiber coupling, what does matching the mode typically refer to? So, in fiber coupling, in the week 11 lectures, we saw something about matching the mode. So, what does it usually mean? So, matching the mode basically means that you are making sure that your beam's focal spot as well as your aperture size is kind of similar. So, matching the mode typically means option correct answer is option B here. Matching the beam's focal spot and entry angle to the fiber's core and numerical aperture. Option B. Question number 8. In a two mirror alignment setup, why is the process described as iterative? In a two mirror alignment setup, why is the process described as iterative? So basically in a two mirror setup, uh, sorry, the process is described as iterative. So we saw this is a direct application of the third question where we see about the intercept. So basically your 2 million alignment setup. So if you adjust the slope, it also adjusts the previous intercept. So it goes on forever. So that's why it's called iterative. So correct answer is option D, because adjusting the slope inevitably shifts the previously set intercept. Question number 9. This I think we have already went through a lot of times. The optical axis is physically defined as what? So optical axis is basically the geometric link connecting the centers of the lenses in the setup. Option A. Yeah. And this is also a very theory-based question. What device was demonstrated as a controller for the laser diode power board in the lab? So if you see the video, the course instructor Dr. Balaji Jayaprakash, he uses a Arduino microcontroller as a controller for the power board. So answer is option C, Arduino microcontroller. So does anyone have any doubts before we start moving on to the uh, next part? Can have 5 or 10 minutes of doubt session before we go to the next part. Okay, so there are no doubts. We'll move on to the uh, previous weeks, that is week 10's problems. So the first question is, what is the main purpose of the tube lens? So what is the main purpose of the tube lens? So we all know that the, any kind of microscope, especially a confocal microscope, has a objective lens, and the objective lens will um, kind of focus your collimated beam into a certain focal point where your sample will be lying. So from that sample, beams will start to diverge, and you have to kind of direct that as a collimated beam to the back focal plane. So to do that, you have to create a hinge point. So for that, need a something called as a tube lens. So the correct answer will be to create an optical hinge about the back focal plane of objective lens. I think we already saw this in the sample questions. Given a scan lens of focal length f1 and a tube lens of focal length f2, what should be the distance between the scan lens and tube lens? So it should be the sum of the focal lengths of the lens, which is f1 plus f2. So this is a theoretical question. Where is a galvanometric mirror placed in a laser scanning microscope? So typically a galvanometric mirror is placed before the scan lens and tube lens. So correct option is option C. Which one of the following is not a limitation of confocal microscope? So there are multiple options here where one deals with fluorescent signals sent as weak because of scattering of light. There are some weak signals captured at the focal point. It needs to have very high intensity of excitation beam in order to function. Spatial resolution is no compared to a multiphoton microscope. So the correct answer here is option C. It needs to have very high intensity of the excitation beam in order to function. So that is not a limitation for confocal microscope. That is actually a limitation for your multiphoton, two photon or a multiphoton microscope, because the probability of two photons striking a single molecule is very rare. You need multiple uh, excitations with the same photon in a molecule to in order for this thing to function, uh, which which is not the case actually in confocal microscope. Yeah. So it's the fifth question is actually a continuation of your fourth question. So in a two-photon excitation process, the emitted fluorescence is directly proportional to the square of intensity, which is actually true. Hence, lesser intensity would be required to excite the sample, which is actually false, because as I said in the previous question, the probability of two photons exciting the same molecule is actually less. So you need more photons. So this more intensity should be required to excite the sample. So the answer is false. Question number 6. Why isn't a pinhole required in multiphoton excitation microscope? So, so generally a pinhole in a multiphoton microscope, what happens is the whatever fluorescence is emitted, it is kind of localized in space. So uh, whatever fluorescence is emitted is kind of specific to that place as well. Uh, that is mean by localization. So therefore, you don't need a specific pinhole kind of arrangement to emit signal out of a specific point in space. So the correct answer is option D. The emitted fluorescence is localized in space. Um, Ultrafast lasers are used in multiphoton microscopes because they do what? So we all know why ultrafast microscopes are used. So they are actually used to generate pulses of high power at shorter regular intervals in the beam. So answer is option C, high power, short regular intervals. Uh, Two slices of the same tissue were stained with fluorophore A and B. A emits in violet emission and B has a red emission. Confocal imaging showed fluorophore A caused drastic structural loss, while B showed good integrity. So, what could be the probable reason? So, could probably be because uh, A showing structural loss can probably because the as we excite A, it may cause A to disintegrate. So, which literally means that A's chemical bonds is kind of breaking on excitation, whereas B showing good integrity just means that there is no effect of light or excitation on B. So the correct option is option D. The excitation light breaks the chemical bonds in case of slice stained with fluorophore A but not B. Uh, this is also a very straightforward question. The disadvantage of critical illumination of sample in microscopy is what? So, except the no disadvantage, all the um, options are valid disadvantages of the critical illumination of the sample. So, your image of the light source is seen with the image of the sample, and it also gives rise to non-uniform illumination of the sample, and it also might heat up the sample. So, all of them are disadvantages of critical illumination. It's also a continuation of your ninth question. Basically, they are asking the working principle of your colors illumination. Yeah. So the correct option is both of them, option A as well as your option C. So sorry, option A and option D. So the working principle of colors illumination is it illuminates the sample by collecting the photons from defocused image formed at the field diaphragm, and it focuses the light photons from the field diaphragm directly onto the sample. Yeah. Question number 11. Which of these lenses will have better resolution? So if you see here, all the options have the same magnification, but the only way in which all the options are differing is with numerical aperture. And we already discussed in the recap that higher the numerical aperture, higher the resolution as well. So our correct option will be option A, 60x magnification with 1.85 numerical aperture. And the last question, which of the following statements justify the Rayleigh scattering? So here the correct options will be um, the Rayleigh scattering depends on the wavelength of incident ray rays, and Rayleigh scattering is inversely proportional to the fourth power of incident wavelength of the light. So options A and B. So that is all for the discussion of the question and answers in week 11. So I'm leaving the I'm leaving the room open for any sort of doubts. If anyone wants to ask any doubts, please feel free to ask. Um, if you don't have any doubts, we can see you in the. I'll see you in the last week of the TA session, which is coming Sunday, uh, 12th April from 3 p.m. to 5 p.m. Yeah, but please feel free to stay in the room and open your mic or for now I can't see anyone in the room, but uh, if you manage to join, or even if you are watching the video in YouTube in recording, please feel free to put your doubts in the comments, or if you manage to join the call now, you can also put it in the chat box, or you can open your mic and ask. Yeah. Okay, if there are no other doubts, I'll see you next Sunday for the last session, 12th April from 3 p.m. to 5 p.m. Thank you.